we have yesterday done this quantization of the fermionic string, in which we started with a worldsheet that had x mu's that mapped into space-time and psi's, psi1 and psi2, with a vector index I, that are just supposed to be thought as additional fields on the worldsheet. And we composed these two fermions that each one lived from 0 to pi, because we were doing open strings, into a big fermion that lived from minus pi to pi, and could be periodic or anti-periodic. And so our conclusion was that we would have a big fermion that went from pi to minus pi, and if it was periodic, we would call this the Ramond sector. And if it's anti-periodic, we would call it the Neves-Schwarz sector. Now, we're going to begin with the Neves-Schwarz sector. We're going to try to understand that sector. And recall this fermion field is, we call it a fermion field. Maybe I should say anti-commuting field. It's anti-commuting quantities, Grassmann odd quantities. So we have these signs that we have to watch out. And therefore, let us begin with NS sector. And we consider an expansion of this field. So this field, psi I of tau and sigma, will have an oscillator expansion. Remember, it's all right moving. We proved last time that this psi of tau and sigma was a function of tau minus sigma. So here is how it will go now. The Neves-Schwarz sector is anti-periodic, so again, we must sum over fractional numbers, like we did for the orbifold. So let's take R, I'll say z plus 1/2, integer plus 1/2, and I'll put e to the minus I r tau minus sigma. That solves the wave equation, and I should put expansion coefficients. And they're going to be B, R, always the same matching here, and I. And these are going to be our oscillators, these things that get quantized and become quantum operators. Now, this is not going to be a full derivation like we did for bosonic strings. We're basically going to state the main facts that can come after a little computation and then use them to understand what this sector is. So you could set up commutation relations and everything, and at the end of the day, these things behave as nice oscillators, and I'll give you the algebra. The algebra is the following: BRI BSJ is equal to delta R plus S, comma 0, delta IJ. So this is an anti-commutator because these are Grassmann odd quantities. Again, sort of the nice usual thing, the R and S, when they add up to 0, you get something, and this must be the same in here. And we're going to have the same conventions if you have the same, no, that's it. We're going to have the same conventions we had before, that B's that have positive R's are annihilation operators, and B's that have negative R's are creation operators. Moreover, one thing that maybe looks different from before is that we used to have Rs and we would put an R here. People usually don't put this R in fermions, so the number operator will look a little different. So what do we have here? So you should imagine that we're quantizing the superstring. So there's going to be sectors. That is, the total Hilbert space, H, of states of the theory is going to have an NS sector and a Ramon sector. And you should imagine them as a box with a collection of states, another separate box with another collection of states, and the total number of states of the theory are these two boxes. But we get them in boxes. So for this thing, to distinguish these things, we're going to build states built on a vacuum. So what is the vacuum going to be, or the ground states? Well, we'll put a P plus P transverse as usual, and we'll put what we call the Neves-Schwarz vacuum. NS, like that, like the ground state in the NS sector, the ground state for these B's. So these B's, the annihilators, kill the state. So the B positives, Br greater than 0 on NS is equal to 0. So that's the vacuum. You could have put, if you wanted, an NS here, but it's clearer to have it written this way. So let's build states. The number operator as well is going to be just the counting of these oscillators in here. So we're going to count them like that and build states. So states with n perp equals 0. Well, if you have no oscillators whatsoever, you can put just the vacuum. So I'll be a little briefer. I'll put NSP. So sometimes we just call it NSP. How about n perp equals 1/2? Well, that's possible because there are oscillators with half integer quantum number here. So we can put here B minus 1/2 I on NSP. That's pretty much the lowest thing you can build. That's 8 states. And if you looked at them, you would say, well, if things work out right, this looks a little like a vector, like a gauge field. Remember, the states of the photon field had a vector index. That's the vector index. You know, it's all a little strange because there's no alpha oscillators, but that's okay. That looks like a vector if it would be massless, and we don't know what's the mass yet. N perp equal 1. What can you build with n perp equal 1? Well, there's not a B minus 1 because these are fractional. But there is a B minus 1/2 and another B minus 1/2. Now, these things are Grassmann odd. So if I chose, for example, the third oscillator here, running from 2 to 9, the critical dimension is 10, and we're going to just write things that I runs from 2 to 9. If you put a 3 here, you cannot put a 3 here because these are anti-commuting variables and it's 0. So you have to put different ones. So you could put an I and a J, and you have to know they must be different. So there's NSP. That's one state. Yes. Sorry? Because the critical dimension of these string theories that I assume already is D equals 10. So you have this indices 0, 1, 2, 3, up to 9. These 2 here are for the light cone, so that all these transverse things, these are always transverse indices, run over 8 values. Yes. Maybe I didn't mention it too importantly, but the superstring works in 10 dimensions. you calculate the it's sort of similar, the m minus I generator, do the algebra, and this time it comes out to 10 because they're fermion contributions. Okay, so you got this. Is there more states here? Any more states that we can build here in the Navier-Schwarz sector at that level? There are. So what can you use to build a state? You have to think a little bit that these boxes, NS and R, but remember, your theory has the fermion and has the X's. And in the Navier-Schwarz sector, you have the X's and the anti-periodic fermion, and in the Ramon sector, you have the periodic fermion and the X's. So what else can we write? Sorry? A, exactly. So you can put, say, an alpha minus 1I on the NSP. How many states there are here? This have different values, so it's like an antisymmetric matrix. So there's 8 times 7 over 2 states here, and these are 8 more. And that's 28 plus 8, 36 states here. Probably it's worth doing the n-perp equal 3/2. What do we get here? Well, we could have 3 of this, b minus 1/2, b minus 1/2, b minus 1/2, I, j, k on the vacuum. We're not writing. You can have b minus 3/2 on the vacuum. Then you can have an alpha minus 1 I times a b minus 1/2 j. That adds up to minus 3/2, and I think you ran out of things now. That's it. No more. We can count them. I won't, but it's nice to count these things. So at the end of the day, what is a state in the Navier-Schwarz sector is this. You multiply from I equal 2 to 9 pi n to infinity, and you can put the alpha n's, lambda n I, and pi from j equal 2 to 9, pi equal r equal 1/2, 3/2, all those little ones, b minus r j to the rho r j acting on NSP. So anything that you could do with the oscillators of the alphas, the x's, you can do. And you have now these negative b's that you can put in all amounts. So that's our list of oscillators and our list of states. Now, we want to understand the masses of these things, and that's a nice thing that we can do. We have the L0 operator and the usual things that give you, if you remember, 1/2 for the bosonic sector. Let me go back to what we have to do usually, alpha minus pi, alpha pi. These kind of formulas are relatively natural, and either one must derive them or you can use them with confidence if you haven't derived them. The idea is to basically learn how to use them. So a mass squared, if you remember when it came from L0 bosonic only for an open string, it was this term, and you had to order these operators because you were summing over all p's, positive and negative. And for each dimension you had an A Neumann that we said was equal to minus 124. And that was the contribution from these ones for each dimension. Now we have to order these things with fractional numbers. And it's the same thing as we had to order for the orbifold. So let me just do it. So at this moment, I will, maybe I can say a couple more things here. Yes, one thing. There's the R in here that doesn't appear here, but that was exactly because the R didn't appear in this formula. That's the way most people write it, so I didn't want to change it. So we have to reorder half of this sum, basically. We have to reorder here the part where R is negative, because when R is negative, BR is a creation operator, and the creation operator shouldn't be to the right. So our problem here is reordering the negative ones. Reorder this part that is 1/2 sum over R equal minus 1/2 minus 3/2, all those, RB minus RB RII. So if we just relabel R for minus R, it's a relabel, you would have 1/2 the sum from R equals 1/2, 3/2, all those, and you would have in front a minus sign. So we just relabel R for minus R. You have a minus 1 for this, and B RI, B minus RI. And this looks more natural. It's just, you see that this needs ordering because you have the negative ones here. So we have to anti-commute this thing. So this thing is going to give a term similar to the positive ones plus an ordering constant. That's the only thing we're basically looking for. So what is the ordering constant? So there's going to be another sum plus the ordering constant is going to be minus 1/2. Now, we're going to have an ordering constant for each value of I, because this commutator here has delta ij there, so you're going to get d minus 2. And over here, we're going to have, I'm sorry, I didn't copy the R. We're going to have the sum over R's. Because the anti-commutator is a Kronecker delta, but the R remains there, and there are d minus 2 of them because you trace over this thing. So this is 1/2 of the sum over the odds, but that's equal to d minus 2. This is 1/2 the sum over the odds, which yesterday we saw it was 1/12. So we get minus 148 times d minus 2. And we've learned something that you then put in a box, that the ordering of every Neves-Schwarz coordinate gives you a minus 148. Because for each of the coordinates that you've reordered, you got a minus 148. For normal oscillators, minus 124 in here. So that's what we have. So what do we have in total? Well, for each coordinate, we have a bosonic contribution and a fermionic contribution. For each I, we have minus 124 from the bosonic part and minus 148 for the anti-commuting part. And that sum is minus 116 for each coordinate. How many coordinates do we have? We have 8 coordinates. So the total A total is 8 for minus 116 equals minus 1/2. All right, so we have an ordering constant of minus 1/2. So we go back to this formula and basically say alpha prime m squared is going to be equal to the number of operators, both for the bosonic and the fermionics, minus the ordering constant of 1/2. And that's very nice, because that actually shows that over here you've got m squared. So I'll put it here, NSP, put a column here, alpha prime m squared. This is minus 1/2, 0, 1/2, 1. So you seem to get some tachyon here. But here is mass 0, so these are going to be gauge fields, Maxwell fields. They're in one-to-one correspondence if you want to put all the indices with P plus, P transpose here, pre-transverse. They're have a Lorentz index, have 0 mass, have the right momenta. These are states of a vector field. And then there are massive states over here. So, yes? This one? This one? This is going to be, well, we'll see. That's going to be a fine state. It's going to be a field with 2 indices. So it's probably going to give you some symmetric massive field and an antisymmetric massive field. It's nothing very famous. You see, anything that is massive has a lot of mass and in string scale mass. So probably you're not terribly interested really in what it is, and its field theory is fairly complicated. Okay, so one more thing we want to discuss here, and then I'll turn to the Ramon sector. Before that, I'll stop a few seconds to let you ask some questions. We're going to introduce a fermion counting number, fermion counting. So we're going to call, it's called the -1 to the f operator, like f being for fermion counting. So if the fermion number is supposed to be 0, for example, this is 1. If it's 2, this is 1. If it's 4, so if there's an even number of fermions, this is +1. But if there's an odd number of fermions, this is -1. So this is a number that characterizes states. So we want to be able to assign a value of -1 to the f to every state in the Navier-Schwarz sector. So for that, we need to give the value of -1 to the f on the ground state. So we'll say that -1 to the f on the Navier-Schwarz ground state will be -1. It's a definition. And then we'll say that -1 to the f, which is counts fermions, anti-commutes with the BRs minus BR I -1 to the f. Sorry, this formula is already. So the -1 to the f is a device, some sort of operator. You write it like that, and you declare it's going to have this algebra. And therefore, it's going to count the number of fermions. The -1 to the f will commute with the alpha n's, will not pick up a sign because the alpha are bosonic. The b's are anti-commuting quantities, so we want to count a sign for this thing. So, for example, here in our formula, this will have -1, well, let's put a table of -1 to the f here. -1 to the f. So we've added the mass and now the -1 to the f. This is -1 because we declared the vacuum to be fermionic. That's a convention, but you can choose that one. This one is going to have these states. If you come with -1 to the f, you get a minus sign as you cross this one by definition, and a minus sign acting in here, so it's a plus. This has a +1. Here it has a -1, because in all of these, either you can just directly hit or you hit it after an even number of b's. So these are all -1s. These are all +1s, and they alternate. So actually, you see that here in this state, here it has n perp equal -1/2. It's the ground state. There's no oscillators. If you jump by 1 unit in n perp, you must have an even number of b's, because the b's are fractional, and you've jumped a unit here. And the same if you jump another one. So that's why these numbers alternate here. And the states of n perp integer n perp integer are fermionic, and the states of n perp half integer are bosonic. The half integer n perp have +1 in -1 to the f, and this one has +1 in -1 to the f. Okay. Oops. We have this up. Okay, Yunji. It's your definition. It's really a definition. You know, in a sense, no, I should just say that it's just a definition. Sorry? Fine. No problem. Yes. Yes. Yeah, but these are all conventions, and these are all issues about 2 dimensions. This is, you see, the B's are not fermions in space-time, and are not fermions because fermions in space-times are totally different things. These things at this moment are worldsheet stuff. So whether we call it a fermion or a boson is regarding the worldsheet conventions at this moment. So we'll leave it like that. That's again, these are anti-commuting objects in the worldsheet, and with respect to space-time, it's not clear what they are yet. Okay. Yeah, I'm sorry, it's a lot of stuff. So let's try to see if we can make sense of this a little later. So Ramon sector. Now, I'm going to do this sort of same thing with the Ramon field. So I'm going to expand it. But this time, the Ramon field, it's a little simpler to expand. n belonging to z, dni e to the minus I n tau minus sigma. So these are integers, and everybody calls the Raymond oscillators with a letter D. So what are your Raymond oscillators? Well, you have D0I, D1I, I'm listing them, D2I, and you have D minus 1I, D minus 2I, D minus 3I. And you could certainly have, well, that this one is going to have a non-vanishing anti-commutator with D1. What we expect, the D2 with D2, and the D0s are sort of left alone. And that creates all kinds of incredible opportunities. You see, that doesn't happen in the B sector. In the B sector, you have B1 half, B3 halves, B minus 1 half, B minus 3 halves. All these are oscillators that contribute mass, and they are matched to each other. Here, there are some oscillators that will not contribute to the mass because they have index of 0. And they're not matched to the rest. So there's something unusual happening here, and that's why the Raymond sector, even though it's integers, it's actually more subtle and more interesting than the Navier-Schwarz sector. It's very unusual. So we have this. What is the anti-commutation relation? DMI dnj will be delta m plus n, comma 0 delta ij. And therefore, that applies even for D0. You have D0i, D0j equal delta ij. And that should remind you of the Clifford algebra. This algebra of gamma matrices, gamma I with gamma j equal 2 eta ij. And suddenly something that starts to smell like spinors are appearing here. Because somehow these D0s probably should be thought as gamma matrices. So we'll see that at this moment. So how do people think of these things? I'll do it very heuristically. It's sort of the intuitive way in which people think about this. You have the D0i's are 8 zero modes. You can view them as paired, just like these are creation, these are annihilation. Between those 8, you can think of 4, call them creation. You form linear combinations. 4 can be thought as creation operators, and 4 can be thought as annihilation operators. So let's call the creation operators psi1, psi2, psi3, and psi4. It's some linear combinations of these ones. And we don't need to get into the details of which combinations there are to understand the structure. But we had 8 zero modes, 4 creation, 4 annihilation. And then we're going to have a vacuum. Vacuum. And the annihilation kill it, but the creation don't. And now here comes the great thing of this vacuum. You see, this vacuum is going to have some energy, its lowest energy state. But as long as you keep adding these oscillators to it, these things don't destroy it, so you can act on it. And these are going to have, since these are zero modes, they're going to have the same energy. They're all going to be degenerate. So you're going to get a multiplicity of vacuum states, something that you never had in the Navier-Schwarz sector. In the Navier-Stokes sector, it's just the NS vacuum, one state. In the bosonic string, one state. But in the Ramond thing, you're now going to get a multiplicity of vacua. So I'm going to write them this way, maybe to be very explicit. You have the Ramond vacuum, this 0. I'll put it here. I'll list it 0. And I'll have here, for example, Xi1 acting on 0, Xi2 acting on 0, Xi3 acting on 0, and Xi4 acting on 0. These are 4 states. They're degenerate with these ones because all these are 0 modes that won't contribute to the number operator. And then I have things like Xi1, Xi2 on the vacuum, and Xi1, Xi3, and Xi1, Xi4, and Xi2, Xi3. There's 6 of them. And Xi2, Xi4, and Xi3, Xi4. So 6. And then I have the things with 3 of them acting on the vacuum. Xi1, Xi2, Xi3 on the vacuum. There are 4 of those. And there are 4 of here. And finally, I have Xi1, Xi2, Xi3, Xi4 acting on the vacuum. That's 1 state. Now, why do I list all of these states? Because I want you to notice that there are states acting on the vacuum with an even number of fermions, and there are 8 of them, and there are 8 in which there are odd number of fermions acting on the vacuum. This we call fermions, but the anti-commuting variables would be a better name at this moment. So we're going to call this the Ramond states, the Ramond ground states RA, all this list, where A goes from 1 to 8. The ones that are even on the vacuum, and there we're going to call RA bar these ones, which have A bar equal 1 up to 8, because there are 8 states. And these have odd number of 0 modes. And here have even number of 0 modes. So the Ramond vacuum, R vacuum with a capital A, is 16 states. And they are composed with RAs and RA bars. This is the birth of a spinner, a real space-time spinner here, in a sense. Look, the Xi's are some linear combinations of the D's, of the D zeros. I'm sorry, the D zeros, the Xi's are a linear combination. So you know how to D zeros transform under Lorentz transformations because they have an index. You can calculate how the Xi transform. There's sum and differences. And then the Lorentz transformations are going to mix all these states. These 8 states are going to transform in a crazy way because they're going to be complicated transformations in which they transform into each other in funny ways. And these ones are also going to transform themselves among themselves. So these are objects that transform in funny ways under Lorentz transformations of space-time. And in fact, they're transforming as spinners of 10 dimensions. We will not discuss spinners in 10 dimensions, but these are objects that have very intricate transformation laws. Okay, we have to do a couple more things in the Ramond sector and then put this thing together. So what about the mass operator? So let me say again that there's a -1 to the f now also in the Ramond sector. We'll declare the RAs to have -1 to the f to be fermionic. And again, that's convention. So minus 1 to the RA is going to have minus 1 times RA. And these are going to be fermionic. And the RA bar are going to be bosonic. The only thing that is important is that they really must be opposite to each other, because one has either an even number of xi's or the other has an odd number of xi's, so they really should be opposite to each other. And again, the minus 1 to the f will anti-commute with any dn, and minus 1 to the f will commute with any alpha n. So again, you're just counting these things. Finally, the mass squared. What is the mass squared operator? Alpha prime m squared, well, p equals 0, alpha minus 1I, alpha pi, plus 1/2 sum over p different from 0, I'm sorry, n over all integers and d minus ni dni. Okay. The mass squared, as usual, has the bosonic contribution. Now the Ramon sector contribution. What does that give you? Well, here we have the issue of ordering again. There's going to be terms, the negative ones, that are badly ordered, because the negative ones will have a d minus n here, and that would be a creation operator, and that's not good. So we have to order the negative ones. Now you would say, look, this has an ANN equal of minus 124. These things just are integrally moded, so maybe they contribute the same. Well, they don't, because of a minus sign that has appeared here. So let's see where it comes. So we have to order the negative ends. So that means that we have minus the things that have to be ordered minus 1/2 n the ni d minus ni. So you look from here, you take the negative n's and change n for minus n. So this goes minus, and this goes like this. So everything comes from here. And here we just have to anti-commute this. So we get minus 1/2 d minus 2 sum over n, positive. And that is minus 112, but there's a minus 1/2 here. So this is plus 124 times d minus 2. So each Ramond fermion, A Ramond, is plus 124. And that's pretty good. That's really very exciting in many ways, because there are equal numbers of bosons as there are fermions here. The I runs over same values, and each one cancels each other. So at the end of the day, the alpha prime m squared is just n perp, and no A. A is equal to 0 here. They cancel for each direction. So let's build states. You know, when you build states, you realize whether you know what you're talking about or not. So let's do that. Okay. I'm going to put a line here. I'm going to put several lines here. And I'm going to put things that are fermions here to the left, and bosons here to the right. So at lowest value of n perp equals 0, we have what fermion states we have? The RAs. These are fermions. And what are the bosons? The RA bars, 8 states of each. Then let's go one level higher. Now n perp, and this is n perp is alpha prime m squared. So this is n perp is really the mass. What n perp comes next? Can we do n perp equal 1/2? Yes or no? Can we use the B oscillators here as well? Can I use the B oscillators here? It's an important question. What does your intuition tell you? Can we use the B oscillators here or not? Think about it. It's really important. Junji, what do you say? No. Any more opinions? Annabelle.
Oh, no,
John? Yeah, that is is something that you should keep well aware. These are separate boxes. The NS vacuum, you can act with B's. There's no meaning even to put a D here, because you're not talking about Ramon vacuum. These are separate boxes, separate worlds. The world of Ramon states, the world of Neves-Schwarz states. On the Ramon vacuum, there's no B's. B's don't exist. It's only because the X's appear in both that seems a little confusing. But in the Neves-Schwarz world, you don't put D's, and in the Ramon world, you don't put B's. So no, we can't use them. So we don't have fractional ones. We begin with 1 here. So what can we do here? I want to construct fermions of this side. So this one will be a fermion. Alpha minus 1I times RA. I want to construct, but there's also, you could put a D minus 1I on something. That would have the right n perp equal 1, some vacuum. But I want it to be a fermion. But this is a fermion already. So if I use this vacuum, I would get a boson. So I must use that vacuum this time. And minus 1 to the F gives you a minus 1 for this and a plus 1 for this. So you're still fine on this side. Sorry, there's so much notation. But here, what do we do? Alpha minus 1I on RA per bar. That's good. That's still a boson. And then D minus 1I on RA. You could go further, but it's probably not worth it at this moment. I'll stop here. And these are massless. This was the great discovery of Ramond. He looked at this and he said, this is unbelievable. It's clear that at each level, there are equal number of bosons and fermions. Because if you have a state like this that has alphas with A, the same state can appear here with alphas and the A bar. If you have a D oscillator here, well, you use RA here and you use RA bar in the other one, or vice versa. So every state that you build here You can copy it to the other side, and you may or may not change the vacuum, but it will exist on the other side. Therefore, he said, this theory has equal number of fermions and bosons in a two-dimensional sense, and this is really two-dimensional supersymmetry. Probably the first appearance of supersymmetry ever. Equal number of things. Yunji. But you have to speak louder. Yes, this is all space-time. What you're asking is space-time interpretation. We're not there yet. But this is basically a plane observation in two-dimensional states. Forget about what is the interpretation of these things. These are fermions in the sense of -1 to the f and bosons in the sense of that. So we'll leave that for a little later. We want to count states, and let's count states for a while now. Count states. Now, I'm running a little late with things, and we'll see that may affect, guys, we're going to tinker with what you're going to do today in the tutorial and what you're going to do for homework. But I probably will run also 8 or 10 minutes after time, but I want to get to some things that we need to know. So counting states, so we leave the Ramon sector and the Neves-Schwarz sector in order to count states more efficiently, because now we really want to count things well. And it's surprising how well you can count things. So you invent something called generating functions. So f of x is going to be a polynomial of x, typically, and we'll write an x to the n, for n equals 0 to infinity. And we will like to put here an to be the number of states with n perp equal n, for example. You know, it's a nice way to make a function. You have any sector of a string theory, and you put a function of x, and for power n, the coefficient here is the number of states that you can construct with n perp equal to that. Suppose you have a world with just one oscillator, A1 dagger only. So I claim that the function f of x in such a world is equal to 1 plus x squared plus x cubed plus x fourth. And why is that? Because, yeah, I can build only one state with 0, that's x to the 0, with 0 n perp, and that's the vacuum. I can build one state with one oscillator, one state with two oscillators, because I just have one oscillator, this A1, on the vacuum, one state with 3 oscillators, and let me just not bore you. That's all you can do if you had just a single oscillator. But this sum is equal to 1 over 1 minus x. Suppose you had the oscillator A2 of string theory only. What can you build? You can build a state with n perp equal 2. So you build 0, A2 dagger on the vacuum, A2 dagger square on the vacuum, and this thing. So the f of x will be equal to 1 for this. This has n perp equal 2, so plus x squared. This has n perp equal 4, so plus x4. And that's 1 over 1 minus x squared. How about if you now wanted to build something using A1 dagger and A2 dagger? What is the generating function for this world in which you use these two oscillators? Well, you should think of it like this, maybe. Let me call this F1 and this F2. So let me write the product, F1 of x times F2 of x. So I'll write the product. So F1 of x, I'll write it here. I'll write 1 plus x, but I will write on top of it the state, A1 dagger on the vacuum, plus x squared, and I remember A1 dagger on the vacuum. That was the state that went there. X cubed, I won't write that anymore. And let me multiply 1 plus x squared is the first one here, and that's A2 dagger on the vacuum. Plus x fourth is A2 dagger squared on the vacuum. Plus, and this multiplication actually is the right way to do things, because if you start multiplying, you sort of get this, the way this is all being done. Suppose when you multiply, you get a term with x to the fourth. And if you think of this product, the state that is built here has n perp equal 4, and it's built with A1, A1, and A2. Or you can get an x4 here that is built with 2 A2s. There's no other way to get an x4. So actually, this thing is doing the right thing. So if you build things using A1 and A2, F12 is really this, is the product of the previous two. So if you get the generating function of any given oscillator, and you start building states using all kinds of oscillators, you just keep multiplying them, which is very nice. Because at this moment, you can do the generating function of the full string, bosonic part of the string. A1 dagger, you're going to use A2 dagger. A3 dagger, you're going to use all of them. So what is the first function? 1 over 1 minus x. What is the second function? 1 over 1 minus x squared. For A3, it will be 1 over 1 minus x cubed. And you continue like that. So the generating function to count all states is f of x is 1 over 1 minus x to the n, product from n equals 1 to infinity. Extremely powerful. You put that into Mathematica and tell it to expand to power of x to the 30. We'll do it in 1 second, and you will have counted how many states there is at the 30th mass level of string theory. Not bad. If you started building the oscillators and counting them, you will spend, for the level 30th, you won't succeed probably, and will spend probably 2 days to do that. So it's very powerful. Now, there's one more thing that is missing for the bosonic string here, is that each A2 really has an I here. So there are 24 of them. But that's no problem. Each one is a different oscillator. So actually, we should for the bosonic string, for F bosonic, now you take the one that you had before. Now you had 1 minus x to the n here. But this was because there's a 1 minus x for the A1s, but there are 24 of the A1s, and there are 24 of the A2s, and 24 of the others. So actually, here goes a 24. And that's it. You've got this. This gives you, for an, the number of states with an perp equals with n perp equal to an. Now, people do one more little change in here. They say, well, remember, n perp is nice, but m squared is nicer. And m squared, or alpha prime m squared, is n perp minus 1 in the bosonic string. So people say, oh, you have an, or a of n, x to the n, where an was the number of states with n perp equal n, but we prefer an a of n, x to the n, where this an is the number of states with alpha prime m squared equal to n. It's a small difference. Alpha prime squared equal to n, or n perp equal to n differ by a factor of 1. So the states in the bosonic string will begin shifted by 1 unit. So it's like shifting x by 1 power. So if you have one state here, for example, you have this f of x is 1 plus 24x plus because it's one tachyon, or one state with n perp equals 0, 24 photon states with n perp equal 1. But if you use the mass squared, this thing should have mass alpha prime m squared equals minus 1. When n perp is 0, this should be minus 1. So the new bosonic partition function, in which you have powers indicating the mass squared, should have a 1 over x in front, pi, to subtract this minus 1 here. N equals 1 to infinity, 1 over 1 minus x to the n to the 24th. This thing is fine, and this gives you 1 over x plus 24 plus, in fact, I'll write it here, plus 324x plus 3200x squared plus 2500, 650 x cubed, and it goes on. So here you have 24 massless states. So because it's x to the 0, and the mass counts that. So we've modified, so let's put this thing again. When you sum over n, you're doing the first oscillator, the second oscillator, the third oscillator, the fourth oscillator. When you sum over 24, you're counting the 24 things. When you divide by x, you're taking into account that alpha m squared is n perp minus 1. You've divided by x. And this is the complete bosonic partition function. This is our rear board. Couple more minutes and we'll round up this, although we'll leave an important punchline for later, for tomorrow. Now, I want to say tomorrow it's our last lecture, and I'll actually have to leave perimeter a little later after that. So if you want to talk or ask me some question or something, we can try to do it mostly today. Tomorrow, half an hour after I lecture, I have to leave perimeter. So it's a little too rushed, but what can we do? Now, let me do the fermionic case, and we'll leave it at that. Now, the fermionic case is easier. It's much easier, because if you have, say, a fermionic oscillator, B minus R, you can build actually only two states. You can build a vacuum and B minus R on the vacuum, but you cannot use it twice, so there's not much you can do with it. So in this sense, the partition, the generating function here is 1 plus x to the r, because this state is just one state with 0 n perp, and here is one state with n perp equal r. So 1 plus x to the r. So what do we have in the fermionic sector, NS sector? We have a B minus 1/2 I, a B minus 3/2 I, and all these B's. So what does it give us? Well, the B minus 1/2 gives us a 1 plus x to the 1/2. The B to the minus 3/2 gives me a 1 plus x to the 3/2. 1 plus x to the 5/2, and goes on. But there are 8 of each one of them, so this is to the power 8. So these are all the states you can make with all the B's of the world. And how much is that? This is the product from n equals 1 to infinity of 1 plus x to the n minus 1/2 to the 8. For n equals 1, 1/2. For n equals 2, 3/2. So that's it. You've counted all the things that you can make with B's. But in the Navier-Stokes sector, you can use also the alphas. And how many alphas are there? So let's try to build the Navier-Stokes sector counting formula. It's not hard. We already have these fermions, n equals 1 to infinity of 1 plus x to the n minus 1/2 to the 8. But we have 8 bosons. You have the alpha minus 1I, the alpha minus 1 minus 2I. And what are those? Those, just as we learned there, are product from n equals 1 to infinity, 1 minus x to the n to the 8, because there are 8 of them, and all of them like that. Finally, we have alpha prime m squared equal n perp minus 1/2 in the Navier-Stokes sector. So we have a shift of minus 1/2. Here, for a shift of minus 1, we had this. For a shift of minus 1/2, you need the square root of x. So the Navier-Stokes sector partition is 1 over square root of x, and now the products are the same one, so you can put a single product, n equals 1 to infinity, of the ratio 1 plus x to the n minus 1/2 over 1 minus x to the n, all to the 8. This formula, again, you put it in Mathematica, and it will give you all states at every mass level. And number theorists love these things because there's all kinds of beautiful properties of that. So you can write, actually, the Ramond one by inspection as well. It's not harder. This time you have d minus 1s, d minus 2s, all fermionic, but with integer numbers here. So the Ramond one, what is it? Well, you would have 8, 1 plus x to the n this time. Not fractional, because they're fermionic, but they're in the numerator, but they're not fractional. 1 plus x to the n over here. For the fermions, 1 minus x to the n for the bosons. You can put a single thing. All of them over 8 values. There's the product from n equals 1 to infinity, fr of x. And there's one more little thing missing. There's no shift of mass squared in the Ramon sector. This is ns. In the Ramon sector, alpha prime m squared is n perp. So there's no extra factor of x needed. But they were all built on this RA. There were 16 ground states. So each state of here is built on any of those states. So you have a 16 in front. This went a little fast, but counting is not difficult. This is sort of fun and easy. Believe me, it's easy, even though it was fast now. You have to practice a little bit. And then there's going to be one interesting thing, whether we'll have space-time supersymmetry. And we'll discuss that thing once we understand these factors a little better tomorrow. So we'll see you later. We'll leave for tomorrow the final buildup of that string theory.